chapter 11. And I have added a moment ago questions from chapter 10. And for this, I didn't want, I know next week is spring break. I didn't want to interfere with the spring break, but it was impossible. So I put it for Monday, the 22nd, right after we come from a spring break. So I apologize, I intruded into a spring break. But since we have, but I feel that I have an argument since we lost 1 week. Okay. So it's only reading on chapter 10, which we are going to discuss today. Okay. So those are already there. If we go here. Assignments. Oh, let me so here they are. This one is all, I don't know why. What is this doing here? Okay, so we do 12 problems, 13Q readings from chapter 11, and 14Q readings from chapter 10. Homework HP. Okay. So please, will you please write your name on the chat so that Mansour can write the roster? Okay, so then so this is the attendance. Okay.
Dr. Ramos, I was there on Thursday.
Hold on. Hold on a minute, please. Okay, so what is your name?
Julio?
Julio Camacho. Were you saying that you were on class last class?
Yeah, I was here Thursday.
Tuesday. No. Today is Wednesday, so you mean?
Yeah, sorry. Yeah, Monday.
Monday?
Yeah. I thought yesterday I even thought it was Sunday. I've been so busy.
Okay. Fine. So now let me show this. Power, no. So we were looking at this. So let's quickly review this. Example 11. We did let me okay, so let's quickly review this. The chapter, okay? Feeders. So here are the classifications of feeders and branch circuits. Okay. Then feeders can be divided in main feeders and sub-feeders. And branch circuits are at the end, to the right, directly to the load. So in power, the circuit is the system of conductors. The system of conductors. So branch circuits are the system of conductors from the last circuit breaker to the equipment, to the utilization equipment. Okay, so here is the definition. Now these are photos of cables. Examples, so ampacity. So we get to the ampacity. So here remember gauge and temperature, ambient temperature. There are two temperatures. One is ambient temperature and the other temperature is conductor temperature. Okay. Now, when we test the cables for short circuits, then we use this table for the total number of cycles and the K factor, which relates asymmetric and symmetric currents. And then we use these plots where we have several cycles, lines, and then on the horizontal, we have the size of the conductor, and on the vertical, we have the short circuit current. So this is the short circuit current that the conductor is able to withstand for a given number of cycles. So this is for aluminum, I guess. There are two. So then we review these examples. Now for voltage drop, so then the system of conductor is represented by the distributed resistance and the distributed reactance. And then we will use this table for that. In this table, we need to calculate the 1000 amp. No, this table gives us 1000 amp feet. Is that right? Values are per 1000 ampere feet. Okay. So this is voltage drop for a single phase line to neutral voltage. So these are examples 11.8 and 11.9 that you can use to solve your problems, okay? For to calculate voltage drop. And then remember, the rule is going to be 3%, no more than 3% voltage drop in a branch circuit, and including, and that goes up to 5%, including the feeder. Okay. Now, some caveats. Loads can be classified as continuous or non-continuous. So if the load is classified as continuous, then we must increase the ampacity by 125%. Okay, then, so then look at this example 11, all right? So on the left fringe says select size of conductor and conduit. Okay, so here is something new, conduit. For the feeder required for the following. So load is 100%, 100 kilowatt, 90% power factor, and is non-continuous. So then we do not require the 125% upgrade. Load is less than 50% ballast type lighting. There are no other loads that cause teraharmonics. So the implication of this is that the neutral will not be considered a current carrying conductor. So then in the conduit, we can consider filling by 3 conductors only, although there is a 4th conductor, which is the neutral, and a 5th conductor, which is the equipment grounding conductor, but those two normally do not carry current, so they are not considered current carrying conductors. So that's the second note on the left. Third, the supply for the length. 5th, short circuit current is 17,000 amp asymmetrical, no, symmetrical. Okay. 1, 2, 3, 4, 5, 6. Feeder over current protection is molded case breaker. So note 5 and note 6 are for testing short circuit current. 7, maximum allowed voltage drop is to be 2%. 8, conductors are copper THW in a steel conduit. So then the solution. First, determine the current in the load. For a 100 kilowatt transformer at 90%, divide by the line-to-line voltage, divide by a square root of 3. So then the normal current is 134 amps. So requirements for ampacity, non-continuous load, 100%, same. Neutral does not count as a 4 current carrying conductor. From table 11.1, conduit minimum size is 10. So let's show table, let's show that table. Let me show you the table. Well, we've seen it several times, okay? I'm sorry. So it's this table. So we have to look at THW, and THW is it's a 75-degree conductor here. So it doesn't say 75-degree conductor. It says THW. So that's the THW. And then we are looking for 134 amps. So then 134 amps is right there. So it says what 1 knot right there. That's what it says in the screen that I'm showing you in A. Then minimum next, the test for short circuit B. So first use the go to the table. We need to go to this table. This table. Okay. So it's a circuit breaker here, the first row. Next, the asymmetric current increases by 1.3 times the K0 factor. So from 17,000, which is the available short circuit current, goes up to 22,100. Next, from figure 1.5. So here is figure 1.5. So we go up on 1.0 here. The second graph, we need to look at the second graph, which is 2 cycles. The second graph is this. So it'd be around 30,000 amps. 30,000 amps. Minimum size is number 1. So 1.0 is okay because it's good for 30,000 amps. And the asymmetric current is 22,000 amps. Okay. Next, voltage drop, C. So then for voltage drop, you need to use this curve now. Table, sorry. So we need to calculate ampere feet. So we have, well, first, maximum allowable voltage drop is 2% of 277. So listen that. It took 277, which is the voltage line to neutral from the 480 volt line to line voltage. So this table is good for phase voltage, okay? So then the maximum allowable percent is 5.54 volts. Now the ampere feet is 134 amps times 250 feet. So that's 33,500. And then it's going to use 33.5. Okay, so maximum volt 554. So he's not looking at the table at all, or what? Okay. So then maximum voltage drop per 1,000 ampere feet is 0.165. So now we need to find 0.165 here. However, we have different conductors, copper or aluminum. So we are in copper. Now in copper, we have different conduits. We have magnetic conduit or non-magnetic conduit. So in this case, a steel conduit. It's a steel conduit, so we need to look on magnetic conduit. Then we have three cases for power factor. So 90% power factor. So then we are in this, we need to look in this column. We need to look in that column for the value of 1.65, which is where? 1.62, right here. 1.62. So this is number one. And we are using 1 knot. So we are okay. Minimum size is number one. However, by ampacity, we need to use 1 knot. Okay. So the conductor must comply with the three requirements: ampacity, short circuit, and voltage drop. So when we made the test for ampacity, we said 1 knot, which is thicker than number one. See, 1 knot is here, is the next one thicker. So then this be fine. Okay, 1 knot. Now something else, the size of conduit. So there is one more table. It says table 11.6. Right here. So we have different size of conduit, inches, the diameter, 1/2, 3/4, 1 inch, 1 1/4, 1 1/2, 2 inches. Then number conductor size, and the table will tell you how many conductors you can use. So we are in 1 knot, and we need to put 3 conductors. Okay. So then it's going to be 1 1/2. 4 conductors, sorry. So it says 4 conductors. So it's going to be 5, like this. So if we put 3 conductors, we can use conduit 1 1/2. If we put up to 5 conductors, we can put conduit number 2. 4 conductors, including the neutral. Okay, good. So that's this example you will need for so more examples for the homework, okay? Overcurrent protection of feeders. Okay. So that's this chapter. So next I want to go back to chapter 10. So let me, okay. So do you have questions? This is for, we have discussed for this homework, okay? For homework 12P, this one. So you have problem 8 and problem 6. By the way, I put the, let me show you where I put the problems if you go to, I want to show you where I put the problems in course materials. Right here. So right here, you can see the problems, all right? This is a copy, that file is a copy of this page. This is in course materials. So this is a copy of this page where we are going to do problem 2, 4, 6, and 8. Okay. That's in, so this page is in course materials. It's not embedded in the homework. I could not embed in the homework, but I put it there. Fine. So now let me go back to chapter 10. Chapter 10 is really very interesting chapter. So let's look at it from this point of view. So let me bring out this. Okay. Chapter 10, grounding and ground fault protection. So after studying this chapter, we will be able to discuss the importance of grounding, recognize the difference between system and equipment grounding. So pay attention. System and equipment grounding. Identify the advantages and disadvantages of ungrounded system. Identify the advantages and disadvantages of grounded systems. Select the points for grounding systems. List the purpose of equipment grounding. Explain the effect of equipment grounding circuit impedance. Select the size of the system and equipment grounding conductors. Identify the characteristic of arcing ground faults. Estimate the damage that can result from arcing ground faults. Explain the methods used for ground fault protection. Discuss the merits of high resistance grounding. So these are very important topics for the reliability of the electric system and also for safety. So let's get started. Let's see, how do I go from here on? Here. Okay, so this diagram shows the two groundings. One is system and the other equipment. Okay, so number one, identify conductor number one on the right here is grounded, is the neutral. The neutral is grounded. Okay, so then the neutral is part of the system of voltages. is part of the system of conductors. So then the system is grounded through the neutral in the secondary of the transformer. So here we have a delta Y transformer. The delta is not grounded, only the secondary through the neutral. Now, we have also number 2, grounding all non-electrical conductive materials that enclose or are adjacent to the energized conductors. So metal enclosures in this diagram are represented by dashed lines, metal enclosures. So those metal enclosures are called non-electrical conductive materials. So they are not supposed to be electrified, but they enclose or are adjacent to the energized conductors. So those metal enclosures have to be grounded through the equipment grounding conductor. Okay, so this is the difference. Next, here we have the first case of, okay, so it says that we can have ungrounded systems. For example, in this delta case, we have ungrounded systems. So the conductors A, B, and C in the top figure are grounded through a virtual capacitance. That distributed capacitance is not a capacitor that we can see. It's a distributed capacitance from the conductors to ground. It's there, but it's not a device that we can see or touch. Okay, so then those conductors are referenced to ground through that capacitance. And therefore, we have an effective neutral point. So if you look at the bottom left B, we have a neutral, a neutral point in the middle of the triangle. So we have that the conductors A, B, C are at a certain phase to neutral voltage. Okay, so that's the one on the left. Now, what happens on the right? You can see on the right that conductor C has been grounded. So conductor C being grounded, then the triangle, all sides of the triangle are lifted so that C is at the level of the ground potential. Okay, so now C is grounded. Now A is, with respect to ground, is at line-to-line voltages. B, with respect to ground, is now at line-to-line voltage. It increased the voltage of A with respect to ground. A before the fault, let's think that a fault occurred and C was grounded. A before the fault, A was at line to neutral voltage. After the fault, A is at line to line voltage. So A and B are stressed. Okay. Fine. So this is the case of ungrounded system. Let's look at the following. Another, okay, so then the conclusion of this diagram is that if C is grounded, then the system can remain operational. The system remain operational as long as A and B can support the stress of going line-to-line voltage. If A and B support that stress, then the system is continue operational. So this is an advantage of ungrounded systems. Now, next, this is another advantage of these ungrounded delta connected systems. Look, if in the left, we have the 3 transformers working. On the right, transformer 3, which is connected between A and C, is missing. Transformer 3 is missing. Only transformer 1 and transformer 2 are operating. So this connection is called open delta operation. And look, with 2 transformers, we can sustain the 3-phase system. So for the secondary, the load will be looking at 3 phases, even though the 3rd transformer is gone. However, it will not be able to deliver 100% power. There'll be a penalty. It will go down to 57%. So then this is another advantage of the delta connection, that if the transformer is connected, 3 transformers, single phase, this is called a transformer bank, then we can have the 3-phase is still working even if one of the single phase transformer is lost. So let me show you, okay, so let me continue. So then, now here are some of the disadvantages of the ungrounded systems. So they are related to distributed capacitance. And if we have grounding through a high inductance, for example, a motor, then we can have a resonance. So the resonance means that these 2 reactances cancel each other. Remember, J capacitance is negative J, inductance reactance is positive JX. So XC and XL can cancel, and then a very high current can circulate, and also through this XL, and therefore the voltage on this motor on the phase conductor can be very high. So that's one disadvantage. So another disadvantage, again, here we have some sort of resonance between distributed capacitance and the reactance. Okay, now look at this diagram. This diagram is interesting, okay? So look at the delta on the top left. So it has some light bulbs with resistors to the center of the delta, and those are, they will show us the phase to line voltage, okay? So those, and then you have those, you have a panel of those lights on dash lines, ABC. You see on the top, a panel ABC with those lights. So it says, normally those 3 lights will be on. However, if phase C is grounded, because of a fault, then C becomes 0 volts. So C lights out. So the ground fault is right here on the right to the bottom. Okay, and the system continues working. So this will tell us that there is a fault in the system. If we do not have these ground detectors, these light detectors, if we don't have this panel of lights, then we will not notice that there is a fault. Okay. Now, in bottom figure, there is a second ground fault on the same phase. So now there is a second ground fault on the same phase. Okay. Then it's locating the first ground fault. So when you have faults, you don't know where they are. You need to open, and then each of them is energized until you detect the fault. So you open all the circuits, and then you energize the first one, and you see there is a fault in that. And then you repair the fault. So the first fault is gone, but then there is still a second fault, and you don't know where it is. You only know that it's in C. So then you close the second switch on the right, and the fault continues there, etc. So you need to open and close until you get to the last and find the fault. Okay. So here in this diagram, again, there are, look, in this diagram on the right, there is a fault on phase A. So that's fine. System continues working. But now there is a fault on second fault on phase C. So then they have, so now we have a line-to-line fault, and then the main breaker is going to operate. Okay. So it's kind of tricky, all right? So then with respect to faults, the best is to use the grounded star. So then this is the secondary. Fine. So we have the neutral, the system ground here. Then we have also on the load. Imagine these are equipment. So now we have a fault on the first fault. So this represents the fault through the so now the fault is going to be conducted. Okay, so on this path, then get connected to the neutral, go back all the way to the transformer, and then to the main breaker. So now then the breaker will operate very quickly, because it is the first fault, but the breaker is feeling the fault because the system is grounded. So this is the second type of second case, grounded systems, 10.0 So this is in page right here, grounded system, page 308. Okay. So then so in this case, okay, system, look. So this, we have the system of conductors in the source, and the neutral is rounded right here. Now, in a branch circuit, we have a panel, and then we have a neutral here, and it says system should not be grounded at a second point. Okay, so only the neutral is grounded at one point, and that is at the secondary of the transformer. Why not? The answer is given here. If a neutral is grounded at a second point, then ground return part will share part of the unbalanced current. So if we ground the system here, then ground is going to conduct part of the neutral current. The normal path of the neutral current is going to be through the neutral conductor, which is going up. Now, if we ground the neutral on a second point, now we are going to have also current through the ground. So that's not correct. For reliability, the idea is perfect controls of the currents. So the current, we control where the currents go, and we do not let the current choose their own path, okay? Because if that happens, then there may be unexpected consequences. So the neutral is provided for the return current, okay? So therefore, we do not ground the neutral a second time. Okay, now, this diagram is about separately derived systems. You see this word here on A, separately derived systems. Okay, so then it says, we have a ground here on the primary transformer. If there are separately derived systems, we can, for example, on the bottom, we can ground again on the neutral, but after the second transformer. So ground each section of the system supplied through its transformer. So in the first case, where the motor or the primary, the neutral is not grounded because it already grounded in the secondary of the primary transformer. So the first case, the two positions, motor and primary of the second transformers, are not separately derived. They are not separately derived. In the bottom part, the secondary of the second transformer are, yes, they are separately derived. So then we can ground again. Okay. So now for this diagram, let's see. Let me rotate this diagram. Yes, we still have time. So I want to rotate this, rotate right. So look, very much detail on this. Let's put some. Okay. So look, let's look at the right. On the right, we have an outlet, a grounded receptacle. So then the plug, we have the three prong plug. So then we have a line and a neutral and a ground. So the dashed lines are for the receptacles, the metal non-electric parts. The all lines which are broken or dashed means that they are the enclosures. Okay, so we have enclosure on the main panel. We have enclosure on the transformer. We have enclosure on the utilization device, and we have another enclosure here on the other utilization device. So here is showing a fault from line 1 to ground. Now, so now look, the ground current goes through the metal raceway from right to left. Then it gets to the enclosure of the distribution panel. Look, the neutral bar in the distribution panel is not grounded. Neutral bar not grounded. So everything has to go through the grounding conductors. So in this case, the raceways are being used as grounded conductors, which is possible. NEC allows that. Then we get the current arrives to the distribution panel. So now from the distribution panel, it must go to the main switchboard. So now it's going to go through the raceway again, through the conduit, metal conduit. So now here we arrive at the main switchboard, and here the neutral is grounded. This is the only point where the neutral is grounded. So then from the equipment grounding bus, it goes to the neutral because neutral is grounded. Then it goes to the transformer. Then it flows to the line that has been fault. And then the main breaker is going to open right here. Or no, there are two breakers, three breakers. So we must have coordination of breakers. So we do not want this breaker on the main switchboard, not the breaker on the distribution. We want the breaker on the distribution panel to open, the one to the right, because of the coordination of, coordination of breakers. Fine. So then I'm going to stop here, but before we go, I want to show you something else. It's a photo of a picture of a transformer here on hold on, 3371 power. Yeah, this one. Look. This transformer, delta delta, it's outside the high bay, 220. So read 225 kVA. Then the impedance, look, 4.8 impedance. Then where are the voltages? The voltages, okay, so three phase, 1 Y 225D 16. Okay, so then here are the connections. We have delta to delta. So then delta primary, H1, H2, H3, 480 volts, 10 kV bill. So kV basic impulse level. So then this means that the transformer can withstand 10 kV, but for a very basic impulse level. So in factory, transformers are tested for the case that a induced voltage, high voltage from a thunderbolt, it's on the line. So they call that basic impulse level. It is so that lightning stroke is very brief, is no more than 50 microseconds, but the transformer should be able to withstand it. Okay. The secondary, look, it's also in delta at 240 volts. Okay. So then look at this. It's really interesting. Let me see, where can I increase this more? Okay, so let's first look at the left. The primary has different tap connections. Okay. So we can move the connection and increase the increase or decrease the number of turns. So look, it's 408 nominal. 408 nominals. But the idea is to maintain 240 on the secondary. However, if we are at the end of a long voltage line, of a long line, and the voltage drop comes down to 444, then if it would be just a simple transformer, the secondary voltage will not be longer 240. But then we can move the taps and decrease the turns ratio so that it maintains 240 volts on the secondary. Now, the second case is this, look, the secondary is delta, okay? And then we have the middle of one of the legs of the transformer has a connection, which is called a X0, and this can be grounded. This can be grounded, and then you can have 120 volts to X1 and 120 volts to X3. And then you can also have between X1 and X2 and the others line-to-line voltages, 240 volts. So this transformer is outside the engineering building to the high bay. Okay, so I have to go now. Thank you very much. So please don't forget to put your name on